Imagine you are on a tall staircase and you want to know how many steps are below you. Instead of counting them yourself, you turn to the person one step down and simply ask them the very same question. How many steps are below you? They ask the next person down, who asks the next. And on it goes, each person passing the exact same question to a smaller staircase until it reaches someone standing on the ground who can answer at once. 0. There is nothing below me. Then the answers travel back up. 0. Then 1 plus 0 is 1. Then 1 plus 1 is 2. Climbing all the way to the top. That is recursion. A task that solves itself by asking a smaller version of itself until it hits a case simple enough to answer outright. Let's make it precise. A function is recursive when, somewhere inside its own body, it calls itself. Here is the classic example. Factorial. Factorial of n means n times n minus 1, all the way down to 1. Watch how few lines it takes. Every real recursive function has two parts. First, the base case, the escape hatch. If n is 1 or less, we do not recurse at all. We just return 1 immediately. Without this, the calls would never stop. Second, the recursive case. Otherwise, we return n times factorial of n minus 1. The crucial detail, the input shrinks. We call ourselves on a smaller number, one step closer to the base case. Move toward the base, always. That is what guarantees the recursion ends. Now the heart of the whole idea, the call stack. When you call factorial of 4, Python does not compute anything yet. It stacks up a frame, a little box holding this call, and then dives deeper. Let's watch the tower grow. You call factorial of 4. 4 is bigger than 1, so it needs 4 times factorial of 3. It cannot finish yet. It parks itself and waits. That triggers factorial of 3, stacked on top. 3 needs factorial of 2. Park it too. Factorial of 2 lands next. 2 needs factorial of 1. Down we go again. Notice the tower growing downward, each frame frozen mid-calculation, waiting on the one below. And now factorial of 1? This is different. 1 is not bigger than 1, so the base case fires no deeper call. It returns 1 directly. Now the tower collapses upward. Factorial of 2 was waiting on that one. It takes it, multiplies. 2 times 1 is 2 and returns to up to the frame above. Factorial of 3 grabs that 2, computes 3 times 2, which is 6, and hands 6 up. And factorial of 4, the very first call, finally gets its answer. 4 times 6 is 24. The tower is empty, and out pops the result. Factorial of 4 is 24. And that is the golden rule of tracing recursion. Going down only stacks up calls. No arithmetic happens yet. All the real work, the multiplying, happens on the way back up, as the stack unwinds. So far, each call made just one deeper call, a single chain. But watch what happens when a call makes 2. The Fibonacci numbers, each is the sum of the 2 before it. So fib of n returns fib of n minus 1 plus fib of n minus 2, with fib of 0 being 0 and fib of 1 being 1. Let's trace fib of 5 as a call tree. Fib of 5 needs fib of 4 and fib of 3, 2 branches. Each of those splits again and again until every branch bottoms out at a 0 or a 1. Green nodes are the base cases. Now unwind, bottom up. Each base returns its value, parents add their two children, and it flows to the top. Fib of 5 is 5. Correct. The sequence is 0, 1, 1, 2, 3, 5. But look closely at this tree. Fib of 3 is computed twice. Fib of 2, 3 separate times. The whole tree here is 15 calls just to reach the answer 5. And it explodes exponentially as n grows. Naive recursion redoes the same work over and over. There has to be a better way. The fix is beautifully simple. Remember answers you have already computed. This is called memoization. In Python, you can add it with a single line above the function, the LRU underscore cache decorator. Now, the first time fib of 3 is asked, it is computed and stored. Every time after, it is handed back instantly for free. Picture a cache beside the function. As each result is computed once, it is written down. Fib of 2 is 1, fib of 3 is 2, fib of 4 is 3, fib of 5 is 5. The tree that once branched into 15 calls now touches each value a single time. Exponential work collapses to linear. Same recursion, same answers, just no wasted repeats. Now, why do I keep hammering on the base case? Let's see what happens without one. Here is factorial with the base case simply deleted. It always recurses. There is no escape hatch. Call factorial of 4, and the tower just keeps growing. 4, 3, 2, 1. But 1 never stops it now. It plunges past into 0, then -1, -2, forever descending, never turning back. Python protects you here. The call stack is finite, about 1,000 frames deep by default, and once you blow past it, the program stops cold with this error. Maximum recursion depth exceeded. A missing or unreachable base case is the number one way recursion goes wrong. Your turn. Here is a new recursive function. If n is 0, it returns 0. Otherwise, it returns n plus f of n minus 1. What does f of 3 return? Pause the video, build the stack in your head. Down to the base, then add on the way back up. I'll wait. Let's trace it together. We stack the calls going down, and nothing is added yet. Down we go. F of 3 needs 3 plus f of 2. F of 2 needs 2 plus f of 1. F of 1 needs 1 plus f of 0. F of 0 hits the base case and returns 0. Now up, f of 1 is 1 plus 0, which is 1. F of 2 is 2 plus 1, which is 3. And f of 3 is 3 plus 3, 6. That is the answer. F of 3 returns 6. If you got 6, which is really 1 plus 2 plus 3, you have understood how the stack builds down and the answer sums back up. Nicely done. One last thing. Anything you can do with recursion, you can also do with a plain loop. Here is factorial both ways. On the left, the recursive version, elegant, self-similar, reads like the definition. On the right, an iterative loop that just multiplies as it goes. Both return 24 for 4. So which should you reach for? The loop is cheaper. It uses a single frame and never risks a stack overflow. The recursion is clearer whenever the problem is naturally self-similar. Walking a tree, divide, and conquer, backtracking. There, recursion mirrors the shape of the problem, and the code almost writes itself. Trap 1. The big one. No base case, or a base case the input never actually reaches. The recursion runs forever and crashes with a recursion error. Always ask, will this condition truly be hit? Trap 2. The recursive call must move toward the base case. Call yourself on a smaller number, a child node, a shorter list. If the input does not shrink, you never arrive at the base. Trap 3. Trying to compute as you descend. Going down only creates calls. The adding and multiplying must use the returned values on the way back up, or you double count and miss branches. And trap 4. Naive recursion can redo the same subproblem endlessly, like Fibonacci. When you see the same call in the tree twice, reach for memoization. Let's lock it all in. Every recursion needs a base case, the escape hatch that answers a small, simple input directly, with no further calls, and a recursive case that reduces the problem to a smaller instance and calls itself, always moving toward the base. Trace it with the call stack. It grows downward as calls pile up, then unwinds upward, and every combination, every add, every multiply happens on the way back up. When calls branch into a tree, watch for repeated work and memoize it. Master the base case, the shrinking input, and the unwinding stack, and recursion turns from mysterious into obvious. That's recursion.